So now we want to take our optimization and constraint equations and put them into one equation, or more specifically, combine the equations and turn the optimization equation into two variables. Well, if we go back and look at our steps 2 and 3, for example 1 of producing a box of maximum volume with 100 square feet of cardboard, here is our constraint equation. Okay, I'll just go ahead and square that off. And here is our optimization equation. So notice the constraint equation has an x and an h in it, and so does volume. Now, a lot of times, actually, it's not going to matter which variable you eliminate. You can still solve the problem either way. We ultimately want to maximize volume. However, when I look at this equation, I want to think about the fact that one variable might be easier to isolate than the other. Okay? One variable might be easier to isolate. I can either isolate x or h. Now, since this has two x's in it, it might just be easier to get the h by itself since there's only one. So for step 4, we want to combine the equations into one equation and turn the optimization equation into two variables. We might as well get h by itself and then substitute that into the volume. So basically what you're doing is you're getting one of the variables by themselves in the constraint equation and then doing substitution to replace that variable in the optimization equation. To get h by itself, we'll subtract x squared and then divide by 4x. And then our volume equation, which is our optimization equation, we can replace h by that. So notice how h is equal to that. It's going to be replaced by that. And if you want to, you can do some simplification. X squared over x is just x up here. And then I can distribute the x into both of these using the distributive property. So it will become 108x minus x cubed over 4. If I want to simplify even further, 108 over 4 is 27x. And then x cubed over 4 just remains x cubed over 4. So again, now I have my optimization equation in terms of two variables, really. We have the volume, which is based on just x. So if I know x in this problem, and going back to what x means, basically if I just know the side lengths of one of these boxes, I can determine my volume, my maximum volume rather. And so we've termed our optimization equation in terms of one variable, and we can take the derivative and figure out which base length of that box will give us the maximum number of volume. We've turned it into two variables for step 4 for example 1. Let's move on to example 2. Example 2 involved using 10 inches of material to create a equilateral triangle and a square, and we will produce a minimum total area. As a reminder, here was our constraint equation, and here was our optimization equation. Now for this particular problem, it seems equally easy to get x or y by itself in the constraint equation, so we can substitute it in for the area, so it won't really matter. For my particular case, I ended up getting y by itself in the constraint equation. So you subtract 3x and divide by 4, and you get y equals 1/4 10 minus 3x. So I'm going to look at my optimization equation, and since since y is equal to 1/4 10 minus 3x, I will replace it with 1/4 10 minus 3x. But it's being squared, so I have to apply the square to the 1/4, which becomes 1/16, and then just keep this as a binomial being squared, since I really don't want to multiply all that out. So now I have my optimization equation in terms of two variables for step 4. And remember, A is what we're trying to optimize, in this case, minimal area based on x, which in this particular problem, based on the side length of the triangle. So I can basically figure out what the length of my triangle should be, side length of my equilateral triangle should be, in order to determine my minimum area, and I can figure out y from there. So that's it for step 4 of getting the optimization equation in terms of two variables. For example 2, let's take a look at example 3. Okay, going back to our apartment building, we want to maximize our monthly profit on our rent, given the fact that as we increase rent, tenants will leave, but that also means we may save in some maintenance costs. As a reminder, here is our constraint equation. Here is our optimization equation. Now this one is actually pretty evident. Now I forgot to mention, I don't know why I didn't mention this in the previous video. In fact, this equation can be simplified down to n equals 55 minus 140 r. And the way that I did that, I might have to show you on a separate paper. Give me 1 second. All right, so the way that I did that was I basically divided each of these terms first by 40, kept the subtraction sign, so it's n equals 30 minus r over 40 minus 50, okay? But then you can see that's going to become plus 50, so you will get, make sure I'm doing this right, 50, no it's not 50, it's okay, it's 25. 1,000 over 40 is 25. But then the minus becomes plus 25. So I get 30 plus 25 is 55 minus r over 40. That's how I came up with my new constraint equation. It's just going to make it easier for substitution's sake. But what I was really getting at is it's pretty simple. Since n is already by itself in the constraint equation, for my optimization equation, I'm just going to replace n with 55 minus 140 over r. And now I have my optimization equation, my total monthly profit, I want it to be maximized, equal to just an equation in terms of, r basically, which r again is, the cost of, make sure I get this correct, rent cost, yes. So basically, again, just kind of alluding to what we're going to be doing here, we are going to be taking the derivative of our optimization equation and figuring out what rent cost will basically optimize our total monthly profit. And we can do that by using some calculus, figuring out the absolute min and max on a given interval. You can FOIL this out, okay, to come up with something a little bit more manageable. So when you FOIL it, you get P equals negative 140 r squared plus 58 r minus 6600. And so that's going to be our optimization equation in terms of two variables for step 4. And we're really halfway, if not more than halfway, done with the problem. We just have to, again, do some calculus. So this is what you want. You want your optimization equation in terms of two variables for step 3. One being what you're optimizing, and the other one, is one of your measurements or one of the figures you're dealing with. In this case, how much you're going to charge for rent. And again, we can go back and read this question to really see why that is. What rent maximizes the monthly profit? So your monthly profit will be based on rent, which is why we get the optimization equation in terms of rent cost. That's it for step 4 of optimization. If you have any other questions about this, let me know.